Hello, we are looking at notes 2.5, which is on exploring polynomial functions and their characteristics. So the first thing that we need to do is define what a polynomial function is. We've been doing a lot of work with polynomial expressions and equations, but we need to define specifically what a polynomial function is. So polynomial function is always going to be in the form f of x equals, and then we've got right here a sub n times x to the n power plus a sub n minus 1 times x to the n minus 1 power, plus all the way, and it just keeps going until we get to a sub 2 times x squared plus a sub 1 times x to the power of 1 plus a sub 0. Okay, but this only works if a sub 1 all the way through a sub n are real numbers. Okay, so we can't have anything called imaginary numbers. So as long as they're real numbers, as long as our coefficients are real numbers, that's one condition that we have. And the n powers, our exponents, have to be whole numbers. Okay, so we're not allowed to have any fractional exponents, any negative exponents. They all have to be positive and whole. Okay, so an example of an exponential function could be something like this. F of x equals 4x cubed minus 5x squared plus 2x minus 7. All my coefficients right here are real numbers, and I can have decimals, I can have radicals, I can have basically anything except for negative square roots, okay, or square roots of negative numbers, I should say. And my exponents are all positive whole numbers. Right here, this is to the power of 0, okay? Now, there are two parent functions that we already know, you guys are already familiar with. The first one is f of x equals x, which is a linear function. So this is something you already know. How is this a polynomial function? Well, it's to the power of 1. So I have a whole number exponent. So that's how I know that it's a polynomial function. And then the other one that we already know is f of x equals x squared, which is our quadratic parent function. Okay? So in this video, we're going to focus more on our cubic, quartic, and quintic functions. So you can probably guess a cubic function would be f of x equals x cubed. So let's go ahead and make our charts, and these are functions that you guys are going to have to memorize just like we did with our parent functions in our first unit. So let's go ahead and figure out what some of these values are going to be. So -3 all the way to +3. But this time, instead of squaring this -3, I'm going to cube it. So -3 cubed, so f of -3 is -3 to the power of 3, so I should get -27. -2 to the power of 3 should give me -8. -1 to the power of 3 should give me -1. 0 to the power of 3 should give me 0. 1 to the power of 3 is 1. 2 cubed is 8. 3 cubed is 27. Notice how, in this example right here, we went from the negatives to the positives. But when we had quadratics, we did not, because when you square a number, you always end up getting a positive answer. Okay, so let's go ahead and set up our axes. So I'm going to label this my x-axis, my y-axis, and then I'm just going to go by 5s. So that's 10, 10, -5, -10, -5, -5 is here, and -10 is there. And then I'm just going to go ahead and graph it out. Now, -3, -27 does not fit, so I'm not going to put it in my graph. -2, -8 would be right here. -1, -1 is right here. 0, 0 is right here. 1, 1 is right here. 2, 8 will go right here. And then we don't have enough room for 327, but we've got an idea of what our cubic function looks like. So this right here is f of x equals x cubed. Okay? So now let's go ahead and talk about our quartic function. So for our quartic function, it's not going to be x to the power of 3, it's going to be x to the power of 4. So let's go ahead and do that. Let's put this together. So I've got x here, I've got f of x here. We're still going to go from -3 to +3. But this time we're going to get some crazier, larger numbers. Okay? So when I do this right here, if I take f of -3 and I raise it to the power of 4, that means -3 multiplied by itself 4 times, so I get positive 81. Notice how when the exponent is even, I get a positive answer right here, okay? That's going to be a key feature of our polynomial functions, okay? -2 raised to the power of 4 is 16. -1 raised to the power of 4 is 1. 0 raised to the power of 4 is 0. 1 raised to the power of 4 is 1, 2 raised to the power of 4 is 16, and 3 raised to the power of 4 is 81. I'm going to set up my axes, but this time I'm going to label it a little bit differently so I can make sure that I can at least fit in more than just a couple points. I'm still going to go by ones on my x-axis, so I'll put 5 here and I'll put 10 here. I'll put -5 here, and I'll put -10 here. But this time I'm gonna go up by 2. So 2, 4, 6, 8, 10. And then that means that this is 20 right here. 2, 4, 6, 8, 10. This is -10 right here. So this is -20. Let's go ahead and graph it out. Again, -381 is too large for me to graph it out, but let's graph out -216. -216 is going to be right here. -1 would be about halfway up right here. 0, 0 would be right here. 1, 1 is here, and 2, 16 is here. 3, 18 is a little bit too high, so we won't be able to fit it. If you notice, our quartic function looks like a quadratic function as the parent function. When you start to transform it, it can get a little wacky, but the parent function looks very similar. Just like I think Aiden said, it's like a super parabola. Yeah, it kind of is, but it just goes up much more rapidly, okay? And then the last parent function we're going to look at is our quintic function, which if you can hopefully maybe guess, you'll realize that it's x to the power of 5. So let's go ahead and make our chart for our quintic function. So x and f of x right here. And we're still going to go from -3 to +3. And when I do this right here, I'm going to figure out f of -3 is -3 raised to the power of 5. So now I've got an odd number of negatives being multiplied together, so this should be -243, because when I multiply 3 by itself, 5 times I get 243, and since it's negative, this will be negative. This should be -32. This should be -1, 0, 1, +32, and then +243, okay? So let's go ahead and label our axes. I still want my x values to go up by 1s, but I want my y values, this time I'm going to have them go up by 3. So 3, 6, 9, 12, 15. We'll put 15 here, and we'll put 30 here. So we've got 1, 2, 3, 4, 5. We'll say this is -15, this is -30. Our points are going to be slightly off the graph, but that's okay. -3, -243 is way down here. I'm not going to graph that out. -2, -32 is a little bit below the graph. I'm still going to put a point there. -1, -1 will be right here. 0, 0 is right here. 1, 1 is right here. And then 2, 32 will be right here. So if you notice, if we have a quintic right here, it looks like a super cubic. Okay, so essentially that's what's going to happen with our polynomial functions. X to the power of 6 is going to look like it is a quadratic function, but it's going to be even steeper, right? If you notice right here, this is steeper than what we would have for our quadratic function, which would look like a little bit more like that, okay? So same thing once we get to x to the power of 7, it will look like this, but it's going to be even skinnier, okay? So let's go ahead and explore that really quickly. And I'm going to graph out my linear function, which is pretty straightforward, no pun intended, okay? And then if I were to take a look at my quadratic function, this is what my quadratic function looks like. I want to compare it to other functions that are that have even exponents. So if you notice right here, this blue graph right here is what it looks like when I have a quartic function right here. So it kind of looks like our parabola right here, but it's just skinnier, right? So let's take a look and see what happens if we have x to the power of 6. Same thing, the higher the exponent, the skinnier it looks. Let's do x to the power of 20. So if you notice, it almost looks like it's flat right here because when I have these values right here raised to the power of 20, the smaller ones don't make that big of a difference, but as I get closer and closer to 1 to the power of 20 is just 1, but as I get closer to 2 to the power of 20 is humongous, right? But they all have the same general shape. So now let's go ahead and see what happens if we have some odd exponents. So if I have x to the power of 3 right here, that's what it looks like. When I have f of x equals x to the power of 5, it looks very similar, but if you notice, it's a little bit skinnier, and as we get closer to 0, it's a little bit closer to the x-axis, right? Let's do the same thing with x to the power of 7. Looks like that, right? X to the power of 9 looks more like that. So it's the same general idea, but each graph is going to be a little bit skinnier, a little bit closer to the x and y axes as we increase our exponents, okay? Okay, so let's summarize some of our findings. So if we have a linear function, we know that our linear function will look like this when it's in the parent function. And the constant difference will only happen once we take the first difference. Okay, and I'll explain to you everything in this column next time I see you guys in class. Just get this down for now, and then we'll go over what this really means by the constant difference. You should have learned this in grade 9 and grade 10 math, but we're going to go over it a little bit more next time I see you guys in class, okay? The domain is going to be all real numbers because it ranges from all x values from negative infinity all the way to positive infinity, okay? Our range, same thing, it goes from negative infinity to positive infinity on our graph, so y is an element of the reals for our range, okay? Now, when I say possible graph right here, what I mean is a possible transformed graph, okay? So, and you guys know what it looks like when we have possible transformed linear functions. We could have different slopes, we could have different y-intercepts. Here's an example of a possible transformed graph, okay? Now, the next one that I want to look at are the quadratic and the quartic examples together. So remember, quadratic is going to be f of x equals x squared, and quartic is going to be f of x equals x to the power of 4. And when we draw a quick sketch of our parent function right here, our quadratic function will look like this, and then our parent function will look very similar for our quartic one right here. And it'll look more like that. But it's essentially the same idea as we saw when we did our Desmos right here, okay? So now that we've talked about that, it's easy to decide what's the domain. Well, the domain works on all of our x values right here. So my domain here is going to be all x values, but my range is only from my, my minimum right here up. This is for the parent function specifically. Remember, transformations will change things around a little bit. So right here, we can say that the domain of our quadratic function is going to be x as an element of the reals, just like the domain of our quartic function is also x as an element of the reals. However, the range for our quadratic function is going to be y is an element of the reals such that y is greater than or equal to 0. Okay, that's key. And here it's going to be y is an element of the reals such that y is also greater than or equal to 0 because we're going based on our minimum value that we have here. Okay, the differences will be constant in a quadratic when we have our second differences. And they'll be constant with our fourth differences for our quartic example, okay? Now, possible graphs, you guys know in a parabola, I can have parabolas that are upside down, I can have parabolas that are shifted over, shifted down, it doesn't matter. So I could have a parabola that looks like this right here, which changes a lot of the features of my graph right here, okay? Now, let's take a look at what happens if we transform a quartic function, and this is going to be a little bit different than what you might expect. So if I have a quartic function, this is an example of a transformed quartic function. And if you notice right here, I can tell that it's quartic just by the fact that it goes down. So that's so this is one section, and then up, here's section 2, here's section 3, here's section 4, it's to the power of 4. But it's not necessarily true that just because there's 4 sections, it's quartic. It means the minimum it could be is quartic. It could be to the power of 6, it could be to the power of 8, it could be to any even power greater than or equal to 4. Okay, so right here, when I do this, a possible graph that I could possibly have might look something like that. Okay. And then now I want to take a look at our cubic functions right here. So let's go ahead and look at what we have for our cubic functions. So cubic and I want to look at quintic together because they're very similar right here. If you notice, the domain can be any x values, and our range is going to be different because remember, with our even exponents, it goes down and then up. Or if it's reflected, it goes up and then down, right? But the end behaviors are going to be the same. However, here, our end behaviors are opposite, okay? It's either always, it's either going to be approaching negative infinity on one side and positive infinity on the other side, or the opposite, okay? So let's go ahead and write down our information for our cubic examples right here. So for our cubic, we are going to just draw a sketch of our parent function. So this is what our cubic parent function looks like. And then our quintic parent function looks very similar. Okay. The third differences are going to be constant for cubic. And then the fifth differences are going to be constant for quintic. And hopefully that should make sense to you because it's based on the exponent right here, because this is f of x equals x to the power of 3, and this is f of x equals x to the power of 5, okay? And remember, we said this is going to be x as an element of the reals for the domain, as well as for the range. Okay, and here, the domain here is still x as an element of the reals, but the range, and the range is also the same. It doesn't change at all because, again, it goes from negative infinity all the way to positive infinity. Okay? Okay, so now let's take a look at some possible transformed graphs for a cubic function. So if I want to look at a cubic function right here, here's an example of a possible transformed graph. It goes up, and then it goes down, and then it goes back up again. So it doesn't necessarily have to go up and then level off and then go up. It can have some turning points right here, which is something we'll be talking about very shortly. Okay, and then if we have a quintic one, the quintic one can do even more. It can go up, and then it can come right back down, and then if I go all the way down here, it can keep going down, and then it'll go up. So it's kind of like a roller coaster right here. And we've got 5 sections right here. That's the maximum number of sections we can have with a quintic. So this is what my graphs would look like if I were to do this right here. Okay, so this right here would look as follows. This is just a possibility. It doesn't necessarily mean it's the only one that can work. Okay, and then this one right here, another possibility, again, doesn't necessarily mean it's the only one that works. Okay, could look like that. But if you notice, it's still covering the all real numbers for the domain and all real numbers for the range, because it's going to negative infinity in one direction and positive infinity to another direction, while this one right here goes to positive infinity in the same on both sides of our graph. Okay. All right. So for characteristics of polynomial functions, we're going to skip this for right now. We're just going to go into our summary that we have here. So on our summary for our end behaviors, I want to talk about the odd degree polynomials that we have going on first here, okay? So if you take a look right here at our first example of odd degree functions right here. So this is our first example, and I just want to observe my end behaviors. So right here, as x goes to negative infinity, y goes to negative infinity. As x goes to positive infinity, y goes to positive infinity, okay? But notice how if I turn this one off and I turn this one on, this time the left side is going to positive infinity and the right side is going to negative infinity. So they're going in opposite directions. So it all has to do with what? It has to do with this leading coefficient. See how here our leading coefficient is 1, right? But in this one right here, our leading coefficient is -1. So because it's -1, it flips it over the x-axis, so it's going to approach opposite directions, okay? So let's go ahead and summarize this for ourselves right here. So when we have a positive leading coefficient, our graph is going to possibly, this is an example, there's a lot of different ways that we can have our graph look, but our graph is going to look as follows, right? This is one example. So what this is telling me that is that as x approaches negative infinity, y is approaching negative infinity as well, okay? And as x approaches positive infinity on this side right here, y is also approaching positive infinity, okay? Well, what happens if we have a negative leading coefficient? Let's go ahead and take a look and see. Right here, so as x approaches, well, first of all, let's look and see what our graph is going to look like. So remember, it's going to go in the opposite direction like this right here. So as x approaches negative infinity, this time y is going to be approaching positive infinity right here, as you can tell right here based on this graph, okay? And then as x approaches positive infinity right here, so as x is going in this direction right here, our y values are getting smaller and smaller. They're getting lower and lower. They're approaching negative infinity, okay? Let's confirm with our quintic examples right here. So if you look right here, in our first function right here, our leading coefficient is positive, so it should start at the bottom right here and then start to go up. With some turns, some possible turns going on, but our end behavior is pretty much going to be the same. So let's just double check. That's true. It starts down at negative infinity and then it goes all the way up. We've got some turning points and then it keeps increasing all the way at the end once it's gone through all of its turning points. Okay? In this example, in example number 2 right here, our leading coefficient is negative. So this time it's going to start at the top, maybe have some turning points, and then it's going to continue all the way down to negative infinity, which is exactly what we have here. And it's going to be true for any exponent, for any degree exponent that is odd. So if our leading term is x to the power of 11, it will follow the same end behaviors. Okay, so now let's go ahead and take a look at what will happen if we have an even degree polynomial. So same thing, it all has to do with our positive leading coefficient. And again, you guys explored this quite a bit with our parabolas when you guys were in grade 10 math. And the same idea applies to really any type of polynomial function that has an even leading degree. Okay, so let's go ahead and take a look at some examples that we have here. So here's just a regular parabola. It opens up because my leading coefficient is positive, right? Once my leading coefficient here is negative, it's going to open down. Okay, if we can turn this on, there we go. Right, so here our leading coefficient is negative, it opens down. So when the leading coefficient is positive, it approaches infinity in both directions. When our leading coefficient is negative, it approaches negative infinity in both directions. Okay, so let's see if that's true for our quartic example. So right here, when I turn this on, it approaches infinity in both directions. We just have a bunch of turning points in the way, but the end behaviors are the same. They're both approaching positive infinity when the leading coefficient is positive. When the leading coefficient is negative, both sides of my graph are approaching negative infinity. Okay, so this all has to do with the types of functions that they are, as well as the exponent that we have. Okay, so if we have a positive leading coefficient, then we know that our graph could look like this, depending on what degree it is and all the transformations that we have going on. But we know for a fact that it's approaching positive infinity on both sides. Okay, so we can say as x approaches positive and negative infinity, and both sides, y is approaching positive infinity. Okay, but if we have a negative leading coefficient, we know that our graph will look more like this right here. And we can say that as x approaches positive and negative infinity on both sides, this time the y is approaching negative infinity. Okay, all right, we've reached a point where this video is now long enough, so we will not do the rest of this chart today, but we'll finish this up next time I see you guys in class. Okay, so don't worry about filling it in. It doesn't need to be done. I just need to have the end behaviors piece filled in, and then otherwise you're good to go.